We'll give people a couple more minutes.
Yes, it's working. Great. We'll just give people a couple more minutes to come in. Okay, good morning. It is morning, I can tell. I hope you all had a good time yesterday, but I guess some people who didn't show up by now. Yeah, I'm sure more will streaming in as we come. So again, my name is Sharon Tu, and I'm the General Chair of ESWEEK 2023, and I would say welcome to the second day of ESWEEK. And I'm sure you all had a good time yesterday. I just took a couple of pictures, put it on here. We had our keynote by Dr. Sarita Advi, and we also have quite a few presentations and paper posters, and as well as all the best paper candidates presentations from yesterday. There's also competition presentations by the three competitions. And I hope you have joined some of them. Actually, there'll be a demo today as well. And you're going to see a lot more things today. So first is what we're going to have our Test of Time Awards. And then we'll have a keynote by Dr. Heike Rio from IBM. And then we'll have more conference presentations and posters as well as our special day program, which have featuring 2 special sessions as well as a panel at the end of the day program. And also we'll have an exciting social event. And that social event, actually, I heard someone was asking, students are allowed. I said, of course, you are our future. So you will all be allowed as long as you register for that 3-day conference. I also want to make a clarification about the preceding access. So if you go to our website, and go to the button that says attend, and under there, there's a ESWEEK publications. You should be able to access all the publications. Yesterday, there were a little bit of glitches. Some of the papers cannot be accessed. That problem has been fixed by the ACM publisher. So I also want to give you, get your attention that we are on social media. So this is by our social media chair, Mitra Nasri. And so take a snapshot and go visit us on LinkedIn and also Twitter. So with that, I'm going to pass the podium to our award chair, Laura Posey, and she will tell us all the exciting awards winners.
Okay. Can you hear me?
Yes.
Okay, thank you. All right, so I'm so happy to be here. Good morning, everyone, also from me. I'm Laura Pozzi from University of Lugano in Switzerland, and I'm so happy to present these Test of Time Awards to you. And these are awards given in recognition of a paper with the highest impact previously presented at one of the ESWEEK conferences. And it's the most prestigious awards given by ESWEEK. So papers that are selected here really have stood the test of time. And since I don't want to go over the time, I want to go directly to present our winners. They will all take a picture with me and with the PC chairs and give a little speech. So we'll start with cases. And the paper which has stood the test of time for cases is predictable programming on a precision timed architecture. You probably know it already, and we are blessed to have so many of the authors here. And the authors are Ben Licky, Isaac Liu, Sunjun Kim, Irem Patel, Stephen Edwards, and Edward Lee. Congratulations.
Thank you, Laura.
Thank you.
Congratulations.
Congratulations. Okay, thank you. Thanks a lot. So we will now have Ben Licky present. Here you go. And the microphone.
All right, thanks everyone. This really takes me back. And I guess we couldn't twist Isaac's arm into giving the presentation, so I'll present. We're kind of the first authors. Little known fact, we put our two co-authors alphabetically, so I'm no more first author than Isaac is. Oh, I'll change it with this, right? So yeah, let's see. So there were, I guess, 4 generations of prep machines. There's the kind of simplest, most rudimentary version that that we all worked on in 2008, and then Isaac actually went on to write his PhD dissertation on the next generation. And I'm not as familiar with Michael Zimmer because he was kind of starting right as I was leaving, but he had another generation, and there was another one that I'm even less familiar with by Jellum et al. Yeah, these are the various different iterations that all kind of followed the same general philosophy, and the unifying ideas were changing the architecture to make the timing more predictable. So instead of speculative execution or something like that, that's very unpredictable, have a thread interleaved pipeline with replicated register sets so that you can have something executed quickly without the unpredictability, instead of like a cache where you don't know what the cache decisions are and there's a lot of unpredictability. Have a software managed scratchpad memory and have the DRAM access be interleaved across the threaded pipeline to hide some of that latency, but in a predictable way. And instead of like the unpredictability of interrupts, have these non-disruptive low latency interrupts. And so I guess one important measure of a work is like not what questions it answers, but what questions it leaves. And in our work, there was a line, we have an enormous amount of future work planned for PRET. And I think that follows out, because there was, even just in Edward's group, there was a lot of future work. I mentioned, Isaac's PhD presentation at the end, but even before that, there were many other works going on in this same area. And even outside of just within our own lab, there were many other people who built things on top of our paper. Here's like some people who cited us who are themselves well cited. And I think, some people might even be here. And sorry, I blazed through it, but thanks, everyone. Yeah.
Thank you, Ben. Thank you. Thank you. Congratulations again. for the cases best paper. Thank you so much also for coming, so many of you, and also thanks to the program chairs who did all the hard work for the selection. All right, so the next one is the ToT award winner for CODIS ISS. And the Test of Time award is given to this paper, Predator, a predictable SDRAM memory controller. And the paper was by Benny Atkinson, Kees Goosen, and Marcus Ringhofer. We'll move down here. Congratulations, congratulations. So let's go there. Swaroop. Congratulations again. So here.
There's the microphone. Thank you very much. It's really an honor to receive this award. And this was actually the first paper I ever wrote as a PhD student, with Kees being my supervisor and Marcus Ringhofer being my first master student. So some of us peak early. I want to start telling you a little bit about the context of this work. So it was back around Y2K when at Philips, they were facing integration challenges for some of the consumer electronic products they were making, in particular set-top boxes. And there were many hardware components being integrated on a system on chip, and they were sharing resources. And that resulted in a lot of interference that made it really hard to satisfy functional, but also non-functional requirements, such as timing. So then the idea was that we could address this problem by having hardware components that have certain properties that could isolate applications from each other to simplify integration, but could also guarantee temporal behavior to satisfy firm or hard real-time requirements. So at Philips Research, they were already looking into this. So they were making and there was work led by Kees on the ethereal network on chip, and Marco Becoy was working on the Hydra processing tiles together with Orlando, who will be giving the next speech. You see how this kind of comes together. But work on an SDRAM controller was missing, and that was really needed to complete the hardware platform, because you had all these IP components and they were basically converging on a single DRAM controller. So the problem then was that we were faced with, we need to be able to provide guarantees on bandwidth and latency, and that is problematic. And that problem is inherent to the architecture of DRAM, because it's an off-chip memory, it has multi-banks, so there's off-chip pins being shared and so on. And only controllers that were really statically scheduled and very rigid could provide meaningful bounds at that time. Now, the problem with DRAM performance is that it depends on a lot of things. It depends really on the state of the DRAM itself. So which rows are open in which banks and how much time since the last refresh. And that basically depends on the history of requests that have been there before. But it's also important how those requests map on the different banks of the DRAM architecture. And of course, the arbiter, the scheduler that decides in which order you would schedule your transactions or your DRAM commands. All these things matter for the timing behavior. So our approach was to say, we start from something that we know that works. So these very rigid, statically scheduled controllers, and we try to add levels of dynamism to that. So we invented what we call a credit-controlled static priority arbiter. So a priority-based arbiter that uses rate regulation. So it had budgets to be able to bound the number of interfering transactions. We come up with the concept of DRAM groups, to take individual DRAM commands and group them together into larger chunks, where we would have more certainty on how much data that was being transferred, but also how much time it would take to execute those groups. And we made sure that there was a straightforward, predictable mapping from the transactions that were scheduled to the groups that would finally execute. So we built a memory controller architecture on these concepts, and we provided that with an analysis that allowed us to provide hard performance guarantee on bandwidth and latency for each of the ports. So that was the start of our research line. As Ben just said, there's always more questions coming out at the end of the paper. And in the end, 6 PhD students graduated within that research line. So for myself, I continued by generalizing this architecture to cover many different DRAM generations and many different arbiters. There was work on making it reconfigurable, improving the average case performance, integrating the memory controller with the interconnect, doing performance analysis using all sorts of different formalisms to see what would work better. There was optimization of the controller settings, but also of arbiter configurations to deliver guarantees. And lastly, also work looking into the energy consumption of DRAM memories. And if you look at all that research that came from this paper in the end, it resulted in more than 30 papers and 2 books, and also the open source tool DRAM Power that has now been integrated into Gem 5 and is used quite extensively in the computer architecture community. And together, that bulk of work has been cited over 2,000 times now. But that was, of course, internal impact, the work that we did ourselves. But if you look at why this paper was impactful on the outside, it was because it was one of the first papers on DRAM controllers specifically for real-time systems. But more would follow after that. So there was work from Barcelona supercomputing centers, from UC Berkeley with Ed Lee and the guys, and also from University of Waterloo. And what you would see is that step by step, people would start making memory controllers that were more and more dynamic, pairing that with an analysis that could analyze the bandwidth and latency in a more flexible way. And after a couple of years, 2016, 2017, much of this field turned into not making your own architectures anymore, but basically trying to configure and analyze more commercial off-the-shelf controllers. Another reason this paper was impactful was because it was a component. It was a hardware component that fit into a bigger picture, one provided by the CompSoc architecture, which is a platform for real-time application. That's work that's led by Case as well. And then you had the bigger picture of processor tiles, network on chip, memory controllers, microkernels, and all the other pieces that you need to ultimately make a system. So there's been many works, of course, in the context of that architecture, but instances of that platform has also been taped out, and versions of this has also been commercialized by a company called Verintech. So that's the story of this paper and where that ultimately led in terms of other memory research and platform research for real-time systems. So thank you very much. We appreciate your citations.
Thank you so much. Congratulations to everyone. Here you go. So now we go to EMSoft, our third conference. And the paper which stood the test of time for EMSoft is scheduling multiple independent hard real-time jobs on a heterogeneous multiprocessor. And the authors are Orlando Moreira, Federico Valente, and Marco Bicoj. So we have Orlando Moreira here. Congratulations. Let's move here. Thank you. So here's your down is ahead.
Okay, thank you very much for this prize. It was kind of unexpected after all of these years. So what was this work about? So Benny already told you about the work, the worries that we had at Philips and afterwards at NXP about how to build systems that actually would be predictable and composable. The version of the problem I focused the most on was related with radio, but of course it could be used in other contexts of real-time systems. And I focused more on the software components. And the intention of the work was that we wanted to actually be able to schedule multiple hard real-time radio codec instances to start and stop independently. They would be running on heterogeneous multiprocessors, including accelerators, DSPs, general purpose cores, and a communication infrastructure that sometimes could be the ethereal network of Case, sometimes could be something else. And of course, we had unpredictability from both the platform and the application. And what we tried to figure out was how to build an abstraction layer and a compilation flow that would allow us to build a multi-radio with predictable timing while allowing the applications to be developed independently from each other. So the approach was actually providing isolation through budget-based resource reservation and arbitration. We assumed we were prescriptive in the sense that we would expect specific arbiters and resource reservation schemes to be used. So like, for instance, the Predator arbiter of Benny, but many others also, and networks on chip like Ethereal, but other components would be possible to use. And we proposed a compilation flow that would compute budgets from for each one of the applications and enforce these budgets at runtime. The key idea was using formal data flow. Originally, it was synchronous data flow, first proposed by Professor Lee. So I guess it's pretty much knitting everything together. SDF to express the radios and allow rigorous modeling of the temporal behavior of each one of the radios independently. So the idea is that in the paper, what we did was the central component of this flow. I don't know why my slide moved a little bit there, so the circle is not in the exact place. The data flow scheduler was the center of the complete flow. That's the point where you actually show how you compile budgets, independent budgets per radio. And we use time slicing, static order per core for each one of the radios. And then because we used SDF for the modeling, we could do temporal analysis every time we take a scheduling decision. So we choose a time slice, we check whether we are still within the timing. We add a static ordering between two actors. We check if we are still within the timing, and like that, we build progressively the schedule using an iterative flow. So it was essentially a constructive approach. We provided the components that you're going to use, both the schedulers that you're allowed to use, the arbiters that you're allowed to use, and the model that you're allowed to use to specify your application. And based on those, you would be able to build a system that provides temporal independence. Now, this paper was not the first paper of my PhD thesis, but was about the third. But it was a very original version of the idea. So afterwards, there were a lot of ideas that had to be improved. Even for the PhD thesis, for instance, we started with synchronous data flow as the model for the applications. But by the time I finished my PhD thesis, I had moved to another model, mode control data flow, because I needed to handle data dynamic behavior. And the model was designed to express the dynamicity specific to radios. For instance, at the same time at the University of Eindhoven that were working with us, they were developing a different data dynamic model that was a scenario-aware data flow that was more generic, but it was not as easy to use as a programming model, only as a analysis model. And Marco, my co-author, was working on another variation, which was variable rate data flow that would allow you to express the dynamicity in video applications. Also in the PhD thesis, we changed. Originally there was an LP formulation for the TDM slicing problem. We changed it to convex that gives much better results. We improved already with a PhD student that worked with me afterwards. We improved the temporal response models for TDM immensely. So we got much more accurate response models and data flow for several schedulers. We added low latency arbiters, because TDM has this problem that in terms of throughput is very good, in terms of latency is not so great. So we had to build other arbiters that would be better for it and include it in the analysis and in the tools. We did analysis of interference. So eventually we extended also with a PhD student the work into fixed priority scheduling, which used to be considered not possible to analyze with something like data flow. And other people work on other problems like extending it with rate monotonic analysis. Actually, I also worked on this on DVFS, low energy, using the same scheduling framework and improved scheduling algorithms. But one concern I had was about industrial adoption. And what I did in the years that followed this work was actually getting the industry to get interested in it. I did it first with a project with Nokia and NXP, where we did a proof of concept on NXP hardware. It actually won a best paper award at the time. It was on NXP hardware, and it allows us to show practically all the features of the flow. But we had always a hurdle that was getting the programmers to follow the data flow construction rules. And then at Ericsson, we expanded the application model to a more variable rate data flow, so mode control data flow, but a more flexible version of it. But what we always saw that would be a problem with this, the results were actually very good, but it was always difficult to get industry adoption because of lack of robust industry-grade, easy-to-use tools. In conclusion, so this paper was key in a much wider effort that we're doing of the time, which to an extent extended also to the work of Kees and Benny. The key idea was using formal data flow to drive the specification analysis and scheduling of applications. The design flow is perfectly functional, it's comprehensive, it solves real problems, but the lack of robust industrial grade, easy to use tooling has always been a barrier of adoption. It's partially adopted, but never fully adopted, which would be very interesting to see. Well, thank you very much for the award. I still hope to see a lot of this coming back because neural networks are a great formalism to use data flow with, and actually currently all the scheduling work I'm doing actually is using, again, data flow over several years without using it. I'm back at using the same techniques. So still a lot to come, to be continued. Thank you very much.
Thank you. Okay, congratulations again to all of the winners of the Test of Time Awards. And we'll just have another clap for everyone. Collective clap. All right, I'd like to invite Heiko for the social event.
Okay, this is just an announcement for the most important event today. Of course, the banquet, the social event. So you are kindly invited to join us. We are going to have a boat tour on this Southern style ship, the Louisiana Star. What you need to know for the moment is that the boarding time is scheduled for 7:30 till 8 o'clock, and the boat will depart at 8 o'clock sharp. Okay, so if you reach the harbor 1 minute later, then bye-bye. So the location where we meet is in the downtown area. Yeah, so please make the trip from TUHH or from your hotel to the downtown harbor region yourself and enjoy the free rides in the transportation tickets that you have received. I would say that you should count 40 to 45 minutes to commute between TUHH and the Landungsbrücken. Okay. So how do you get there from TUHH? We are over here on the campus, have a walk as usual to the local train station over here. That takes 5 minutes. There you can hop onto the S3 local train in the direction of Pinneberg, and this brings you directly to the Landungsbrücken. Yeah, so you jump out of the train over here, and then, as indicated in the Google map, you can take a walk to the destination where the ship will be. Yeah, all of you are kindly invited. So all persons who have registered for 3 days conference or higher are invited. It does not matter whether you have a student registration or professional registration, or whether you are IEEE or ACM member. Just come and join us. Yes, if you don't have registered, then of course, have a walk to the registration desk downstairs, use the computers to register there, and you can also purchase additional banquet tickets. So I'm looking forward to meeting you this evening. And having said that, I would like to hand over to Aviral, who will introduce our today's keynote speaker.
Thank you. Okay, so next is our keynote speech for today. May or may not be, because the topic is scaling quantum computing. So, okay, so do we have a speech or not? Okay, but our keynote speaker is Dr. Heike Riel. She's a IBM fellow and head of Science of Quantum and Information Technologies and lead of IBM Research Quantum EMEA. She leads the Science of Quantum and Information Technologies department aiming to create scientific and technological breakthroughs in quantum computing technologies, physics of artificial intelligence, nanoscience and nanotechnology, and to explore new directions of computing. And she has an amazing set of expertise. So I'll just read some part of it. She has a master's in physics from Erlangen-Nuremberg. And then she has a PhD from University of Beirut and MBA from Henley Business College. And she is a member of Leopoldina, German National Academy of Sciences and Swiss Academy of Engineering Sciences. She was awarded the APS David Alder Lectureship Award in the field of material physics and applied physics of the Swiss Physical Society. And she also has many other awards, which I think are too long a list to mention, but please honor Miss Dr. Yu.
Thank you very much.
Stop sharing and then go share.
What happens now? It's still the wrong thing.
Maybe there's a switch.
No, that's not.
Stop sharing and share. Go to the play.
Okay, I can.
It's there.
Oh, it's there. Oh my God. Okay. I don't know. I think it's here. Somehow it worked before. Which, this one?
Yeah.
Okay, wonderful. But now, okay. Okay, I think that may not work because I use this one. Okay, so very good morning. I'm very happy to be here and present about quantum computing. It's a bit of different topic than what you typically probably do in your work. And therefore, I would like to guide you through the work which we do on quantum computing and how we scale it up, what the status of quantum computing is, and also, yeah.
We're still not sharing this.
Oh, we're not sharing the screen? Okay, then I may need to end it again, right?
Let's just end it here.
Yeah, and I need to then
Do sharing.
okay, and then so let's
And then we can do that.
hopefully come to the. Now we are in the good.
Yeah.
Now we are in good mode. Okay. Yes. So it's a new topic. It's a new type of computing which we are working on. And however, we are not only working on quantum computing because as we all know, the general processor has quite evolved. And for the future in solving all the problems of increasing the performance of computing and also reducing the power consumption of computing, which is very much on your topic also, we are not only working on quantum computing, but of course also on increasing the performance and lower the power consumption of classical computing, and also using a new type of computing, AI hardware, which I'm sure you are all aware and you are utilizing in your new systems that you're built. Because with all the new workloads which we have on the artificial intelligence, the big data workloads, hardware for artificial intelligence is one component. And our task is, as we see, also bringing all these components together
like quantum computing, classical computing, and the hardware for artificial intelligence in order to create the future of computing. Because the consumer, and in some of the discussions it was heard before, the industry, the consumer doesn't care of what hardware is used. They want to have a solution. They want to have a system which works. They want to have their problem solved. They don't care what hardware we use. And it is fascinating to look back, like the 75 years back when the transistor was demonstrated for the first time. And we see all this evolution which happened if we just think a few moments about this. And also all the systems which you're building, you can develop what's going into robotics, what's going into small things, what's going into big things. And this has led to a lot of different things on the transistor side, a lot of innovation the industry was able to develop. And of course, the FinFETs, that now the nanosheets are coming into play. And there also right now works on creating vertical transistors. And there is a lot of things to come on the classical world. And there was already a lot which happened on the classical world to increase and to kind of fuel the performance and the new application types which we have. And this has led to these big computers which just broke the exascale barrier last year, which are very, very important for simulations and for a lot of our work which we're doing, because simulating means speed, it means faster innovation. And the more we can simulate, the higher the innovation rate could also be. And on the other side, on all these gadgets which have been developed in the meanwhile, which we're using and which are helping in our daily life and have really also changed how we live. But so we have all these computers, we have all these gadgets, there are still a lot of problems which we have to solve. And the question is also, how can technology help, and how can also a new type of computing help in solving some of these problems? And I've brought here some like 4 examples of where today classical computing can actually not really provide exact solutions. And the first example is actually the fertilizer area. We have seen over the last 2 years where the energy price increased, that also fertilizer increased a lot. Because to produce fertilizer, to produce the ammonia, takes about 2 to 3% of the world's energy consumption using the Haber-Bosch process. And so we have found, although doing a lot of research in chemistry and material science over the last years, not a new process which can do ammonia creation and synthesis at temperatures at room temperature, although we know that enzymes exist who can do this. On the other hand, catalysts, also a big challenge of creating new catalysts which work at lower temperature, who do things more energy efficient, and also improving optimization models, right? With all these data which we are creating, we want to actually use the data to optimize our systems. But optimization problems, actually, the complexity increases exponentially, and it's often not solvable exactly. And also in medicine, there are many problems which we cannot solve classically by having the challenge that really calculating the exact energy spectrum of molecules doesn't work today, because the complexity, again, the quantum problem, it increases the calculation power for even small molecules. You would need to build computers which are classical computers, which are larger than the number of atoms on Earth. So it's impossible. And therefore, there is a lot of hope and a lot of work which is currently done on developing quantum computers. And already by looking at the picture, you see that these computers, they look very, very different. You have here, actually, what you see is mainly the fridge. And only here at the bottoms, you have the quantum processor. And all the rest is kind of used for the signaling, for the routing, for the cooling, because the computation happens at 10 to 15 millikelvin. And so you have different cooling stages. You have the the lines going down in order to provide the microwave pulses, which are used to control and to initialize the states and to read out the final result of the computation. So it's a radically new approach which makes use of the laws of quantum physics. And let's dive a bit in and look at the analogy between the classical compute and the quantum compute. And in the classical computer, as you know and use on a daily basis, there is a bit which can be 0 and 1. And at each stage in your calculation, you know whether you have a 0 or a 1 in your bit. And you have the circuits, the logic circuits, and you have a set of gate operations, which then is the unit of computation and allows you also to build universal quantum computers, classical computers, sorry. The next step is now the quantum computer. And here we are working with quantum bits. Quantum bits are more complex because they are based on the laws of quantum physics. And in principle, it's here, as you see, the mass helps a lot to understand it. So you have two states, 0 state, the ground state, and the first excited state 1. And you have a superposition, which actually is your quantum state. And therefore you can present all the points on the so-called Bloch sphere. And thus you see already that your quantum bit allows you to have to store much more information in the quantum bit than in a bit. And then you have a strange phenomena like the entanglement and also interference, which then helps you to create new algorithms which make use of qubits, entanglement, etc., in order to reach big computational spaces you can create. And then an analogy to the classical circuit, you also have a quantum circuit. And what you see here are actually, it's an indication of one qubit here and another qubit here. And then along this timeline, you have different gate operations which you can apply to your qubit. And so here you entangle the 2 qubits. Here you rotate the arrow on your in 1 qubit on your sphere. You entangle it again with the next one, etc. And then at the end, you do a measurement and you get a kind of a probability for being in a certain state. And so we work actually also with probabilities here. And so you see it's very different. And this difference leads to the fact that the performance also completely scales differently. The performance actually scales like 2 to the power of n, where n is the number of qubits, which says if you add 1 qubit, then theoretically you can double the performance. And that's, of course, a big scaling law. So today we did not reach it yet because we are not yet in the error-corrected world. So we still have errors in a qubit. But I will talk a bit more later about errors and where we are. So if we look at it theoretically, then in order to, what you see here in this table is actually an indication of how many bits you need in order to simulate the behavior of a qubit. And you see already that if you want to simulate qubits, then you need quite a few bits. So for 2, it's okay. It also goes down like 20, you already need 17 megabytes. And then if you're at 35, already 550 gigabytes. And if you go in the range of 100, then 2 to the power of n. And the number of bits you need in order to simulate it is more than you can build a computer on the Earth. And so there is a clear line of 100 qubits, and these are ideal qubits, that here in this regime, quantum computing really can become very, very powerful to solve problems which we cannot solve with classical computers today and will not be able to solve also in the future. So what are these problems? And so quantum computers will not replace classical computers in the foreseeable future. So you will still do transactional type of calculations with a classical computer, but there are certain problems which quantum computers can solve much better than classical computers. And one easy example, which probably everyone knows, is that doing multiplication is very easy for a classical computer, but then doing the factorization is very difficult for a classical computer because you have to sequentially go through every number and check every number whether it's a prime factor. And this is, however, Shor has founded an algorithm where you can do this in almost no time if you have a universal quantum computer with like many qubits. And so there are other problems like simulation of nature, like simulating molecules which are governed and based on the quantum physics. So to mimic them on quantum computers also helps you because they represent the same physics. And this helps in physics problems, in chemistry, quantum chemistry, simulating molecules, doing material science, etc. Then there is another type of problem, which is the mathematics and database structure. So for example, machine learning or factoring, which I mentioned, and also ranking and the symmetric groups where quantum computers can help. And another big area, which is of high interest, is actually optimization problems, also like risk analysis, option pricing, and others. And if you go in the different industries, then you find in all the different industries such type of problems. And so this is why quantum computing is also very interesting to solve these big problems. Not every speed up is the same. For some of these problems, you can get an exponential speed up. For example, for quantum machine learning models, but also for the factorization. For some, you get a greater than polynomial speed up. And for example, here, these are heuristics where we have proven in this case that for quantum Monte Carlo simulations, you can get a quadratic speed up. So one has to look into detail, and a lot of research is currently going on in order to check where the biggest benefit is and how to approach these problems. So now let me switch on to how are these systems look like and how do we build those systems. And there I want to show you a picture of a lab, because this is where quantum computers have been developed for the last like 40 years, or let's say 20 years, because the first 20 years were theory, and then experimentalists were told how to build a qubit, and then physicists went out to find different physical systems of where qubits can be built. And so you see here actually the fridge where now it's under vacuum. There's a lot of electronics which you need in order to generate the pulses and also do all the control of these errors in the Bloch sphere. But what you see is that quantum computers here, they have moved in the last 7 years from the lab environment, so from a true physics lab where only physicists work with quantum computers, to a data center where they are meanwhile housed and where you can get access through the cloud. So already since 7 years, our quantum computers are actually on the cloud available. And you can log in, you can test, you can run algorithms, you can get familiar with quantum computers. And in the last 7 years, we have worked quite hard to scale these systems, to also create a community of researchers who can use these computers and accelerate thus also the research and the development of applications and algorithms. So there are meanwhile more than 2,100 publications published using these quantum computers. And there are also many users which are already having access and are using quantum computers, more than 450. And we have meanwhile also deployed more than 60 systems with increasing number of qubits. So when you look at such a system, then it's really building a full new system from the scratch. And this means you start with the qubits, the quantum processor, the component and the wiring, the cryogenic platform to cool down the processor, the compiler, the error mitigation, error correction, but also the software has to be developed that people who are not physicists, who are computer scientists, who are chemists, who are engineers, can then get access and can use Python to program such computers in an easy manner and use also libraries of things which are there in order to solve the problems they want to solve. Bringing this in the cloud, the compute architecture, because typically for solving a problem, you need not only a quantum computer, but also a classical computer to work together. First, you need to go through an interface to a classical computer, and then you have run the quantum computer. But there are also algorithms where you do part in a classical system, another part in a quantum system. Middleware and of course also theory and algorithms and applications. So on all these fronts, there's a lot of activity we are working on in order to build these systems. So quantum computers, you need the qubits, as I've indicated. And for a qubit, you have a few criteria. You can implement them actually in several different physical implementations. So you could use ions because they have a ground state and excited state you can use. You can also use neutral atoms. You can use photons. You can use spins, individual spins as an up and down spin for the qubit. You can use also other solid state qubits like Andreev qubits, Majorana qubits, etc., or also NV centers. These are nitrogen vacancies in quantum, in diamond, or phosphor in silicon, etc. And what we are using are actually superconducting qubits. And these superconducting qubits, they are, there's a lot of knowledge already about the system. It's a, I'll show you on the next chart. It's actually a tunnel junction, a Josephson junction between a superconducting metal, an insulator, and a superconducting metal. And what you see here is kind of one of the early chips, which has 8 qubits. And you see here, that's a superconducting qubit. It's about 600 micrometer in dimension. And what you have is like a shunt, the Josephson junctions in the middle, where you have here a zoom in. So these are the 2 metal lines. And on the cross section, you have then an insulator in between. And here you have the shunting capacitance. And then you have all these lines, the microwave resonators, which are then used to connect qubits and control qubits and read out the result. So these 2 areas, so in principle, what we build is an artificial atom. That's, you have the ground state, the first excited state. And the Josephson junction is actually a non-linear inductor. If you look at this, these schematics, you have the Josephson junction here and the capacitance, and then you can get your anharmonic energy spectrum, which allows you to have now a ground state and a first excited state and an energy in between, which is different to the next level, because you only wanted to control these 2 with your microwave frequency. You don't want to go into the upper states because that's a loss mechanism you want to avoid. So the difference between the 0 and the 1 ground state is about 5 gigahertz. So that's the microwave pulses which we are using in this regime. And you see also that the energy is 240 millikelvin, which means if you want to control this very well, you better are at lower temperature in order to differentiate the 2 states. And then the next building block is a superconducting microwave resonator. And this is now an harmonic oscillator. And this is used for readout of qubit states or also connecting qubits and also as a noise filter. So that's the basics. So how do we program now? We use a classical computer to program this. It goes through the cloud. It then goes to the, you create your algorithm. You then implement this algorithm into microwave pulses that you can rotate your error on the Bloch sphere. And then you let the different gate operations done on your quantum processor and you get the result back. So now let's move on and see, okay, if we want to increase the performance of quantum computers, we better know how we measure them. And so we identified the metrics to measure the performance of quantum computing and also be able to compare different types and implementations of quantum computers, which is also very important for the user. So we have identified one, this is scale, so the number of qubits, but that's by far not enough. You also need a high quality of qubits. So the circuit fidelity is very important. And then also the speed is very important. So how fast does the consumer or the one, when you have a problem to be solved, how long does it take in order to get the solution? So let us now focus on the scale, and I will show you where we are and where we started. So actually in 2016, we had a 5-qubit processor. And now let me see whether this runs. Yes. And last year, we have demonstrated a 433-qubit processor. And we have every year since 2019, we were able to actually to increase the number of qubits on our processors. And you see they have all bird names, starting with falcon, then hummingbird, osprey, and eagle, sorry, with 127 qubits, and osprey last year in November. And you see that end of this year, there is supposed to be another one which is coming up. So when we look at these processors, then, yeah, oops, goes wrong. Yes, I want to, because it's not like that you can just easily increase the number of qubits on a processor. There are from each of these generations of different processors, there were major key steps which we had to demonstrate in order to build it. And for the first one, the Falcon, very important was to control the qubit frequency. And when you build a Josephson junction, you have a tunnel junction, which is very sensitive. The resistance is very sensitive, and the resistance determines the frequency. And we had a big spread of frequencies, which doesn't allow you to then scale up to 1,000 qubits. So we had to find a post-process in order to tune the frequency of these qubits to a narrower distribution. And then for the second one, we had to, okay, you increase the number of qubits, you have to read them out. We implemented multiplexing. And for Eagle, this was a really big step. We went to a new package, which means that when you have more than 100 qubits, you have a problem in individually controlling them or addressing them in the plane. So we had to go to a 3D package where we have multi-level wiring and through substrate vias implemented. And of course, from the semiconductor industry, that's quite known, but doing this at 10 millikelvin and with superconducting Josephson junctions and lines, and also with the microwave hygiene which you need, it's a bit of a bigger problem. And with Osprey, I will show you later, when you have many lines, control lines going down in your fridge, it's getting very dense. And it's also getting very costly. And it's getting very timely or time consuming to screw down all these lines which you need. So you have to come up with new things. And this was the Flex IO, which we demonstrated last year. So you see for each of these steps, there is an important technology which we had to develop in order to build it. And so this is how it looks like on the 3D version. You have the qubit layer, and then you have the resonator layer. And then here what you see is like the multi-level wiring layer. And all this is then coming together in the package. So when you look at the qubit layout, then this is a layout which we are using for the qubit. So each of these white dots here is one of the 433 qubits. And they are connected in the so-called heavy hex layout. So I mentioned before already that when you squeeze more qubits in it in your fridge, then you need to these lines are getting very dense, and you see they're also kind of hand screwed. This is not really scalable, and therefore we implemented the so-called flex IOs, these flex cables, which allow us then to scale up to higher number of qubits by having now these bulky lines implemented in these flex cables. The other part is also the electronics. When we started in 2016, we have 5 qubits. And for these 5 qubits, we took off-the-shelf instruments, which we bought. And so it's quite bulky and it's also quite costly. And so we started also to then develop our own electronics that we can control our qubits and get the dedicated performance which we need, and not like a flexible lab instrument, right? And so we were able to then have with our Gen 1 electronics, where we needed then a full rack for 20 qubits. For the Gen 2 electronics, we had another full racks for the 40 qubits. And then for the Generation 3, which we implemented last year, we could then actually already have 400 qubits controlled with like a third of a rack. And currently, we are also working on integrating this even further. by using and checking, testing also to bring some of the control electronics also on integrated on CMOS, and then bring this down to 4 Kelvin. So studying then also how CMOS behaves at 4 Kelvin, and building up then the design is an important part. And so what we have demonstrated here already, that you see also how the miniaturization went further, right? And so with this CMOS controller, we already demonstrated that it works and that we can do a 2-qubit randomized benchmarking with CMOS controllers. So now let me move on to the quality, which is a very, very important one, because even if you scale your qubits, we need to further improve the quality of the qubit, means reducing the error rate these qubits have. And there are different parts which actually go in the quality factor. It's also the electronics, but it's a lot also the qubit, but also how you control the things. And what you see here is the coherence time, which is a very important factor also. And you see the coherence time as a function of the years. And you can imagine when in 1999, the coherence time was nanoseconds, right? I mean, this is not worth thinking about quantum computing in using it and applying it. But you also see on this logarithmic scale that the coherence times have improved quite a bit. And actually recently we have also hit this barrier and have coherence times of more than milliseconds, as I will show you in one of the next slides. And there have been a lot of innovations from the material side, from the device architecture side, increased understanding, increased fabrication methods also. And all this has helped actually to increase the coherence times over orders of magnitude. And there will be further improvements. And I show you here also an example how, we try to improve also on fast cycles, which means what you see here is actually the Eagle processor and the Falcon processor. Eagle is 127, Falcon is 27. And R1 or R5 means it's kind of the revision. When we build a chip, it's a first revision. When we then do improvements in the same design, etc., then we get to higher revision. So it's the same base design, but we may improve on the fabrication part, right? And so you see that with Eagle R1, we already had the same time as Falcon R5. And then you can imagine we did further learnings from the chip which we produced and implemented these further learnings in a very fast manner, that with Eagle revision 3, we are already hitting like the 300 to 400 microseconds. And so we were able to achieve fast coherence time improvements also. And we, of course, also have test chips. So the other were measured on the processor, but these are like test chips where we also do fast cycles. And here you see examples of that in test devices. We already reach millisecond coherence times. And that's, of course, important to have like in the range of millisecond coherence time, because then also the error correction becomes feasible. Then gate fidelity is a very important part, that when you change your error on your block sphere, right? When you tune it, when you control it, when you apply your gate operation, that your gate operation also does what you want. And this is the so-called gate fidelity or error rate. And important is actually the 2-qubit gate error when you entangle qubits. And you see also here that with time and with improvements, we are able to now reach like 7 times 10 to the minus 4 of gate fidelity. And we are further working, of course, to further reduce. But all these are now coming, or these parameters are coming into a regime that we can also test error correction. Speed, another big important parameter. And here, not only the qubit or the quantum processor is important, which is intrinsically very important, but also the entire compute architecture, how you, what your compiler does, how you interact through the cloud. So all this is very important here. And the superconducting qubits have one big advantage, that the gate operations are intrinsically fast. There are other implementations which you have seen before, which are intrinsically slow. And over the last years, again, also here, we were able to improve like code pipelining or control systems, or we reduced the overhead drives and embedded software. We implemented pipelining of the compilation execution and also parametric compilation, which helped to actually boost also here the speed. So now let me kind of summarize these things into our roadmap. What we put out a couple of years back is actually a roadmap of what we want to demonstrate on the hardware side and also on the software side, what capabilities we want to provide to our users and to the community in order to use quantum computers. And you saw here, I'm already mentioned the hardware part, but you see that we also developed the software that people really can use quantum computers in an easy fashion. And what we have categorized is kind of 3 types of software developers, like the kernel developer, where you develop the circuits and Qiskit runtime or dynamic circuits, other capabilities, which directly interact then with the hardware, and you have to know how the quantum computer and the superconducting qubits work in order to implement this. Then on top, you have the algorithm developer. Here these are actually developing new algorithms based on the quantum circuits, which are delivered by the kernel developers. And then on top, they're still missing a bit here, but there's coming soon, the model developers, which just want to solve this optimization problem. They may use already their chemistry, their optimization software or chemistry software, and the quantum engine is just below, and they just use libraries, etc. So when we move on, you see that this year, what is our task this year? Towards the end of the year, what we want to demonstrate across the full stack. So one is the Condor chips, which is the first chip above 1,000 qubits. So there's only one chip, or there are so far not many have demonstrated that there are chips above 100, but we now want to demonstrate above 1,000. There is also then on the algorithms developer, the quantum serverless, easy access also through the cloud, and also quantum prototype quantum software as a service. And one very interesting part is actually here below, because we actually start to make multi-processors. And why this? Because for scaling up, we need also to find ways of how can we scale up in a different way than just adding or making the silicon larger. And this is a way where we connect different quantum processors in a first step classically. So we use a classical communication and universal bus. And so there's a controller, but this allows us actually to use dynamic circuits, which means that you can make different gate operations and be able to actually go, depending on the result in between, you can change the next gate operation. And this is called dynamic circuits, and it will help then also to reduce and shrink the depth which you need in order to solve certain problems. And the next step, the next year, we have again also here, we want to demonstrate gross bill. This is also a processor which consists of 3 different quantum processors, but they are connected with a quantum bus. And so this processor then appears to the outside world, to the user, as one big quantum processor. And then we also connect different chips in a way with longer quantum links in Flamingo. And there is then also some error suppression and mitigation coming in. So I mentioned this already, that you connect then different chips with a so-called quantum link, and it appears to the outside world as one quantum processor, as a large one. And then beyond these type of things which we have here to connect quantum processors, that allows us to actually scale further up and reach in 2025 quantum processor above 4,000 qubits. And this modular approach and the toolbox which we are building here on modularity can help us then also to scale up to 10,000 and 100,000 of qubits. And that's something what we have also announced this year, that in 2033, we want to build a system with more than 100,000 qubits. So it's quite a challenging and quite a steep slope of increasing the number of qubits on these processors. So now let me move on and explain a bit also on the algorithm side. Because as you see, the quantum processors are still small. They still have errors. And they still have a limited depth of quantum computation. So this means the number of circuits you can apply. And however, what I find very, very interesting is that the algorithm developer, by looking into these methods, have found also ways of how they can divide kind of bigger problems of today into smaller problems, and have these then run in parallel on quantum processors, or one part is on a quantum processor, the other part is on the classical, and you combine this and later together. And these are three different methods of how to kind of divide a bigger problem into smaller problems and solve them and put it together. One is called embedding, because what you do here is, let's assume you have a molecule and there is only a certain part which is highly entangled. And you pick this highly entangled part to solve it on your quantum processor, and the rest you can kind of solve classically and then add the solution together. And in this way, circuit cutting, where you then have your quantum circuit, and you see then there are regions which are less entangled, and these you can then also split and divide on the different processors which are run in parallel, and then can put the solution together afterwards. And these things are called circuit knitting, and there's currently a full fleet of things which are developed in order to cut down bigger problems and solve them then already on the available hardware today. So now I would like to spend a few minutes on talking about errors, because errors appear everywhere. They are in classical, we all know there are many methods of how to work with errors in the classical systems. But in quantum systems, there are also errors which appear, and we have to learn dealing with these errors. And they can appear at the initialization stage of your quantum bit, at the gate operations, but also at the measurement at the end. And quantum error correction is a bit more problematic than classical systems, because in classical systems, you can, for example, just copy your information and do then a majority vote on, that's the easiest one. Of course, there are more sophisticated error correction methods, but this kind of copying of your information does not work with quantum information. It does not work with qubits. So there is a no cloning theory, which says that you cannot copy quantum information, because as soon as you measure it, you change it. And therefore, you need to come up with a different way, which is a bit more cumbersome. And therefore, one example would be like a repetition code that does not work, but you can use parity checks. So you can use other qubits around in order to check the parity and then identify then in which state your intended qubit actually is, your target qubit. And so you have then these white are the data qubits, the bit parity check and the phase parity check, because you also have a phase and a bit and the bit. So you have a bit flip errors or phase flip errors, and those you have to measure and you'll be able to correct. So that's a bit more complex. You need many more qubits. And so it creates a large overhead. The overhead is not so easy to say, because it depends also on your fidelity and also the layout that you use. So there is quite a lot of research currently going on error correction, and it's so far there is a lot of research and tests, etc., and it has been proven that it works. But still, there is some of the methods which are used today, they have a large overhead, and there are now theories which are there to work with smaller overheads. So a lot of things going on. But there is actually another very interesting way, which is not error correction, but error mitigation. And this is something which allows, hopefully, to demonstrate quantum advantage also before we can fully error correct the systems. And quantum advantage, what we call quantum advantage is that we can use a quantum computer for something which creates value in the industry. And this could be on of course, calculating a problem which a classical computer cannot calculate, calculating faster, calculating it with better accuracy, or doing it at lower energy consumption. And so in this plot, what you see here is actually the differences between quantum error correction, classical computer, and quantum error mitigation. So what is shown here is the simulation cost versus the third quantum circuit complexity. And then let's take an optimization problem. And the optimization problem on a classical computer would scale exponentially in the simulation cost. Using quantum error correction, you have at the beginning a very high overhead. So it doesn't make sense. Only later when you have when you come in this regime, because you have a different scaling, as I mentioned at the beginning already, for quantum computing. However, there's a regime actually in between where you can do quantum error mitigation, which means you need a bit more overhead, but not as much as error correction. And you can thus achieve a noise-free result at the end. And that's something which we are working on since a couple of years. And our goal is actually to then come into this regime where we have an advantage compared to classical computing, and where we have less overhead than using quantum fully quantum corrected methods. And so error mitigation works in, there are different approaches also how to do error mitigation. One is to do many measurements and do some post-processing. And another one is actually here called probabilistic error cancellations. You learn your error and then you actually apply the inverse. And in this way, zero noise extrapolation is another way where you actually apply, you increase your error, you learn how your error affects the result, and then you extrapolate to zero error. And this is something which we have demonstrated like a couple of years back with like a 5-qubit chip. And just recently, we have demonstrated this with a 127-qubit chip that we have learned the noise of the chip and we're able to utilize and to kind of mitigate it out of the calculation and thus get noise-free results after the calculation. And I just want to spend another minute that we have here took a competition with a classical HPC at Lawrence Livermore National Berkeley Laboratory. And we actually looked at the magnetization of using the transverse field Ising spin lattice problem and looked at the global magnetization, which is observable here. And we started out by doing this with a number of qubits where we still could calculate it classically and simulate it classically, which is above 100 qubits no longer possible. And you see here the mitigated and the unmitigated result. And you see that the mitigated result agrees with the exact calculation. And then we have increased the challenge, right? We have increased the number of qubits which are part of the calculation. So in this one, 31 qubits, 37 qubits, 68 qubits, which is still possible to actually simulate. And you see that the mitigated result is always agreeing with the exactly calculated result. The unmitigated is going off. And you see there are also approximation methods, which actually at a certain point will no longer work. And then when we go above 127 to 127 qubits, you see exactly it's no longer verifiable. And the approximation methods which were used here, they actually do not work. And but interestingly, after the publication of the paper 3 weeks later, there were 3 improved approximation methods, which then, shown here, which could then go into a regime where these approximation methods, which have been improved, disagree also by 20%. but it's really exciting times because now quantum computers are competing with HPCs already for certain problems. And with this, I would like to actually close and say that next year we will provide a compute capability which is called 100 times 100, which means we have 100 qubits, we have a depth of 100, and this will be calculated in 1 day. And the challenge on the community is now, think about a problem which you can map to this compute capability, and perhaps this then shows quantum advantage. So with this, I would like to thank you very much for listening. Thank you.
Time for some questions.
Sorry? Yes, you're right. Okay. So thank you for this presentation. Very interesting field. I got many questions, but I restrict to one or two. So I think that you mentioned that you had already a chip last year, which is Eagle.
Sorry, I didn't get.
You had a chip
Yes.
with 100 something qubits. And then this year you already have something with 400 qubits. And then you
Yes.
plan to move to thousands of qubits.
Okay, so last year we demonstrated 400. This year we want to move to 1,000.
Yes.
Mhm.
But I think I missed the point of why you need to simulate so many qubits, because you mentioned that with already 100 qubits in the first few slides, you can actually simulate all the atoms in the world, you said. So why there's the need to simulate more than 100 or 200 qubits?
So today, as I mentioned, the qubits still have error, and the scaling up to the power of n doesn't work. It only works with fully error-corrected qubits. So what you need is, in principle, fully error-corrected qubit. That's what I mentioned in the errors, but you have a large overhead also for then creating a logic qubit compared to a physical qubit. So what we have is 433 physical qubits, but not 433 logical qubits.
I see. So, okay. So in general, how many qubits you think you need in the current situation of the, let's say, reliability of these qubits to simulate all the atoms in the universe?
So that's a fully moving target, because currently the error correction methods, some of them, they still have a very large overhead, but the community is actually doing a lot in order to reduce the overhead. On the other hand, the better your qubits are and the less error they have, the less you need to correct. So there is a lot of moving targets right now.
Okay, I stop here to let
Yeah.
others.
So the idea, however, is that with this error mitigation method, you can really learn the errors, and then you can mitigate these errors, which gives you a bit of an overhead, but not as much as the full error correction. And the hope is that with this mitigation, we can then soon demonstrate a problem which can be solved better than a classical computer. And that's where, this kind of this competition with the HPC, where right now we are really in a regime where you come close to demonstrating something which a classical computer cannot do.
Okay, thank you. Any more questions? Yes.
Thank you very much for this very insightful talk. So compared to classical computing, there might be different sources of errors in the computation. But in quantum computing, is the source of error, is the nature of the qubit? This is my first question.
I'm not sure whether I fully get it, sorry, but the acoustics is a bit bad. So
the nature of errors, like if we talk about classic computing, in classic computing, there might be different sources of errors. There might be bit flips, there might be precision errors and things like that. But if we ignore all those phenomena in the classical computing, like about the bit flips and the precision kind of things, then we can say that the classic computer, the bits representation, is it in itself an accurate representation? In qubits, the source of error is the nature of the qubit is a source of error in quantum computing?
No, it's not the nature.
Because like you mentioned about errors in quantum computing.
Okay.
So is this source of error, is it coming from the nature of the qubit, the way that we represent qubit?
No, the source of error in the qubit has many different ways, but it's not the intrinsics of the qubit. It's when you apply a microwave pulse to change the superposition, right? I mean, you can imagine the Bloch sphere, where your qubit has a certain, your vector has a certain direction. And then with a microwave pulse, you want to change that vector.
Yeah.
Right. Then depending, there may be influences from the from charges which are around. There may be your electronic pulse is not ideal. So these are type of things which can happen.
And you also mentioned about like
and the coherence time, of course, because the coherence time is also the length of the average length of how long a qubit will remain in the quantum state. So all these are errors which come in, and then it's as I said, it can influence the bit, or it can influence the phase.
And you also mentioned something about like in classical computing, if we represent 1 kilobits, they can be represented with 5 qubit or something like that.
I'm not sure whether I fully understand.
So
Had a table in
yes, a table is in principle a simulation, right? In this table, what you do is you have you take a qubit, and then it's an ideal qubit without errors, and then you can simulate it classically.
yeah,
Because the behaviors, for example, you up to now with an HPC, you can simulate about 55 or 65 qubits, the behavior.
so is there something like any concept, for example, like in classic computing, if we are doing something with 1 kilobit kind of precision or 8-bit precision or any kind of precision, how many qubits are required to get the same accuracy as we get in the classic computing because of the nature of qubits? Because like when you compare the total number of states represented by classic computing versus qubit, is there also a concept where you mention about the accuracy that is given by classic computing? So how many qubits would be required to get the same accuracy?
I'm not sure. Perhaps we do that offline. I'm not so sure whether.
Saying like
Yeah.
there is floating point numbers that have 32 bits or
Yes.
double precision 64 bits. So what is the accuracy of qubit? I think.
Okay, the accuracy of qubit in that sense is a bit different because you work with statistics, right? You also have to do your measurements many times, and then you get a distribution. And your algorithm, your quantum algorithm, you have to tune in a way that the quantum interference is used to increase the probability of your right result and reduce the probability of the wrong result.
Okay, now it's my chance for trouble. Sharon. Sharon, please.
That was a great talk, as I expected. So my question, since this is an embedded system conference, do you foresee one day these quantum computing platform could be used in the embedded system environment? Because right now everything is going into the cloud.
I expected this question, Sharon. No, I think, quantum computing is at an early stage. I always compare it like the end of 60s with the classical compute, right? Because, I mean, we just started. We just have a few number of qubits. We are understanding how they work with each other, etc., and we are trying to create advantage. So all these systems right now, you can interact just with an API. So in that regard, it's very simple. Of course, these systems are not small, right? They are not yet that you can put them on a layout or on a PCB, right? That does not yet work. Whether this will work in perhaps 50, 60 years, I wouldn't say no, because there are systems like qubit systems, which also could work at room temperature, that you don't need cooling. On the other hand, also cooling methods on chip are increasing. So there are many different ways of how to do it. But the NV centers, for example, they work also at room temperature. Today, they are mostly used actually for sensing. But I think it still takes some time until you get it on a PCB board.
Hey, I thank you all for going over time with us. But since Laura has been so good to me, I'll let her have the last question.
Thank you, appreciate it. Thanks very much for the talk. So in this is kind of related to Sharon. So in computer science, it's been always very important to raise the level of abstraction so that programmers didn't need to know the intricacies of
Yes.
architectures. And in one of your slides, I think you mentioned, but maybe I understood badly, that programmers will need to understand the underlying intricacies. So I wanted
Okay,
to see
yes.
if you, even though we are in early stage, do you think that there will be the possibility of raising the level of abstractions also in quantum computing
So-
later on?
Yes, thank you for the question, because that's exactly what I meant, right? Because here for the kernel developer, that's kind of, you need to look from the bottom to the top, right? The kernel developer is someone who better understands how to program the chip directly, because he has to come up with the microwave pulses. But then on top, again, here already, you in the algorithm development, you need to understand a bit of the math of quantum, because you want to develop algorithms which make use of the quantum physics.
Yeah.
But then if you go on top here, the model developer, they do not care about the one below. They have an algorithm, they have a problem they want to solve, and they can then, oh, I want to use this algorithm, this quantum algorithm, and then it's just a quantum engine which they can plug in.
Okay, thank you.
Yeah.
Mhm.
But you see, as you see, it's a bit of a timeline delay, because first these tools have to be developed that they can use be here, and then they can use be by the model developer. But the model developer is, does not need to understand the physics behind. And currently already you can program the quantum computers with Python. We have an open source software called Qiskit. There are also already many examples of how to program it, and you can solve like an optimization problems, let's say a max cut problem with like 20, a code of 20 lines.
Let me call Sharon to present the memento.
This is the important part.
Yeah, this is the important part. The picture.
Oh,
has to
wow.
be-
Custom made souvenir from Hamburg.
Oh, wow. Thank you very much, Sharon. Thank you. Thank you, everyone. Thank you. Thank you.
Thank you.
Hold it, that it's not
Yeah.
falling down.
We'll make sure it's right.
Yeah, we'll give you enough.
I think now it's time for coffee break, and then there is a session.